Right, this is lesson 3.3, optimization with linear programming, take 2. We're going to find the maximum and minimum values of functions over a region and solve real-world optimization problems using linear programming. So let's go ahead and just talk about what linear programming is and the methods for finding both minimum and maximum values of the function over a given system of inequalities, with each inequality representing a constraint. And so we'll see some examples below and what that means. So after the system's graphed, which we've been doing lately, so that's not anything new, we're going to have some vertices of the solution set that are called the feasible region. So this region is going to be basically the region creating those points that we're going to test to see which one's the minimum and the maximum. So feasible meaning possible region here. So bounded and unbounded. So what bounded means is it's an enclosed feasible region, and that's here on the left. So it's enclosed. Unbounded is this picture over here on the right where it's open, or it goes on forever, kind of in this below region down here. So to optimize, which is what we're going to do, we're going to seek the best price, meaning we want the minimum cost and we want the maximum profit. So we're going to go ahead and find those through this method below. So let's just first go ahead and plot these lines on our graph here to the right. So we do need to change that last one into slope-intercept form, subtract x. So y is greater than or equal to negative x plus 2. So plotting our point going through the x-axis at 5 would be this line here, solid line. Going through the y-axis at 4, solid line. And then we are going to, and you can shade as you go. I'm going to shade at the end. And then start at 2, move down 1 over 1, down 1 over 1, draw that line. So I want everything that is less than 5. So that's going to be everything shaded over here. So kind of just do some quick little shadings so you can see. And then we want everything shaded below that horizontal line. And then we want everything shaded above that line that's... So where is our region that has both green, red, and blue? And that's that middle of that triangle. So that's the part that should be bolded the darkest. So I'm just going to fill that in there. There we go. There's our region that overlaps. So we're going to find our minimum and maximum. And how we do that is we identify these points, the vertices or vertex points, vertices, and then we're going to plug them in to our function for this region. So I'm going to do that over here to the left where I kind of have things already sort of set up. So I have the form. I'm going to plug in my x, plug in my y for these 3 coordinates. So I'm going to first just identify those coordinates. It would be negative 2, 4. It would be 5, 4. And then this one down here would be 5, negative 3. All right, so let's go ahead and plug those points in. So negative 2, 4, 5, 4, and 5, 3. It's 4. All right, so we get negative 6 minus 8, which is negative 14. Here we get 15 minus 8, which is 7. And here 15 minus 6, which is 11. All right, let me double check my points here. Negative 2, yep, there we go. Oh, this one was a negative 3, and I accidentally put a positive 3. There we go. So that should have been a plus 6. So we should wind up with minus 2, there we go. 21. There we go. Watch those negatives. All right, now let's identify our maximum and our minimum. So here's our minimum for sure, negative 14, and then our maximum 21. So we can write them over here. So the coordinates that we used were negative 2, 4 for our minimum, and our maximum down here was 5, negative 3. And our maximum and minimum values, and that's what we wanted, maximum, minimum. All right, go ahead and look at the next example on your own. So those do need to be changed into slope-intercept form first before you graph, and then shade, and then go ahead and identify those vertex points, plug it in, and find your minimum and maximum. So I'd really like for you to pause the video and try that one on your own. You can always hit play if you need a little help along the way. Alrighty, so let's go ahead and look at that next example. So here, if you haven't graphed it, here are your 3 changed into slope-intercept form. So if you needed help with that, get those down, pause, and then graph them. Alright, here's what the shading should look like. So if you struggled with the graphing and the shading, check your answer there. And then the next is going to be the plugging in. So we plugged in these 2 points here, negative 2, 0, and 0, negative 2. So there is no maximum because this is going on forever, so we're really just looking for the minimum here. So when we plug in these 2 points into our function, we get negative 4 and negative 6. So our minimum is going to be that negative 6. So minimum at 0, negative 2, and that's going to give us negative 6. So this point right here was our minimum. All right, let's take a look at an example that walks us through step by step. So we've got a couple different steps. It's very similar to things we did above, only we're actually going to write the inequalities this time and then solve it. So it's important to go through and to highlight those important pieces. So landscaping company has crews who mow lawns and prune shrubbery. Company schedules 1 hour for mowing, that's important, and 3 hours for pruning. Each crew is scheduled no more than 2 pruning jobs, so that's important. Each crew's schedule is set up for a maximum of 9 hours per day. On average, they charge $40 to mow and $100 to prune, $120, excuse me, to prune. Find the combination of mowing and pruning that will maximize the income and make them the most money. All right, so first just define the variables. So I'm going to pick an X and a Y. I'm going to pick mowing since it's first, just give that the X, and Y for pruning. All right, our next step is going to be to write our equations. So let's go ahead and write, our inequalities. So we had the mowing as 1 hour and the pruning for 3 hours. So I'm going to have a 1x, or just an x, and a 3 hours for the pruning, which was my y. And then they talked about hours and how they could not work more than 9 hours per day. So this total has to be less than or equal to 9, since hours, hours, hours should all be in the same inequality. The other restriction that we had was the 2 pruning jobs per day. They can't do more than 2. So that was my y, and that has to be less than or equal to 2. So I can't have more than 2 pruning jobs. And then when we talk about real world situations, we're going to talk about positives, so they can't do negative jobs. So we're going to have the restrictions of x greater than or equal to 0 and y greater than or equal to 0. Basically just sticking with that first quadrant so that our values are positives. So let's go ahead and graph this. So we have our 2 lines. Now we have to change this one into slope-intercept form. So subtract your x and then divide by 3. So y is less than or equal to negative 1/3 x plus 3. So that's where my line here is starting at 3, down 1 over 3, down 1 over 3, and so forth. So that's that line there, solid. Going through the y-axis at 2, solid line. And then these, we just kind of know they're cutting us off from anything in these other quadrants. So can just kind of cover there and then just ignore this side. So we want to look at just this positive region here. So we're going to shade next. We're going to shade less than and less than. So that's just going to be everything below both of these lines. So just this region all in here. So again, we're ignoring all this stuff. So we look for our points, which are going to be here. Get rid of that green point. Highlight them in blue here. And then on the axis here, and then on the axis here. So we're just looking at this positive quadrant. So where those, there we go, that kind of helps. So there's our 4 points. So let's identify those 4 points. They would be 0, 0, 0, 2, 9, 0, and 3, 2. So there's our 4 points that we have. We're going to try those. We're going to plug those in, but we first need to write our function. Now this function has to do with the money. So we said $40 per mowing job and $120 for pruning. So that would be a 40x and $120y for the amount of money they're making per job. So that's what that function would look like. Now we're going to try each of these points in this, and you can make a table. Sometimes that helps. But we want to plug in the 3 for x, the 2 for y, and we would wind up with 360. Plug in the 9 for x, the 0 for y, we would get 360. 0 and 0 is going to get me 0. 0 in for x, 2 in for y, we'd get 240. So that's the amount of money they're making for those different types of jobs. So which one is the greatest? Well, the 360s are the greatest, so both 3, 2, and 9, 0. So what do those mean, the 3, 2, and the 9, 0? Remember, the first coordinate was my x, which stands for mowing. The second was y for pruning. So that would mean 3 mowings and 2 prunings would get them $360. And the 9 mowings and 0 prunings would also get them $360. So either type would get them the same amount, which is the maximum profit.